In the last video, we defined what we call conjugate directions, ones that are not orthogonal. And for our problem of a quadratic function and minimizing it, we calculated that conjugate direction. So today we're going to complete that calculation and determine the trajectory in the conjugate direction and minimize along that trajectory and see where that gets us. And then I'll provide a little overview of the sort of geometric interpretation of the conjugate gradient descent and why it works so well. Thanks. Okay, so last time we started talking about conjugate directions, and we're doing it for this function here, these contours that are given x and y. And we showed that it improved, so this is the red line here, are these conjugate directions. Just draw over this a bit. Was defined here. So we defined a conjugate direction S2, and we have to keep in common the gradient descent direction for the first direction, because obviously you need two directions to form conjugacy. So what we're going to see now is we're going to take this new direction, this S2. So S2, remember, was we calculated as -1, 2, and we're going to now plug that into the minimization steps. That's the main task for today, is to repeat the minimization step now along this new trajectory defined by the conjugate direction rather than the gradient descent direction, and see where that gets us. So we're going to repeat step 2, if you like, but now using S2 from conjugacy relationship. So we now construct x3 is x2 plus alpha s2. Okay, alpha in this case is equal to alpha 2. We're just dropping the subscript on the alpha just to make it a little bit easier. And x2 before was 1, 0. That's what we had before. And s2 was minus, so s2, remember, is -1, 2. So that gives this plus minus alpha times 2 alpha. So that equals 1 minus alpha 2 alpha. Okay, so this is called the trajectory stage of the step, if you like, and then we minimize along the trajectory. So that's our trajectory now is a different function of alpha than it was with the gradient descent. So we now need to substitute x3 into f and minimize with respect to alpha. Let me determine what alpha is. So let's just write x3 up here. 1 minus alpha and 2 alpha. And of course those are going to define the x values you're going to feed into your function, and your y values you're going to feed into your function. And remember also that your function of f of x equals 2x squared plus 2xy plus 2y squared minus 4x minus 6y. So all we're doing is taking the x, it's 1 minus alpha, plugging it into there. Y is 2 alpha, plugging it into there, and then we're going to minimize. So what we're going to do is set up the whole thing. We're going to d by the alpha of f of x3 is going to equal 0. That's ultimately going to equal 0. Let's just remove that bit for the timing. Oh, I'm going to rewrite the x3 as well. equals 0 implies d by d alpha, or you could write it as upright alphas as well. It's just a function of alpha at this stage, is substituting all the bits in, and this is the sort of slightly complicated thing, but you just need to keep tabs of everything. So 2x squared becomes 2 1 minus alpha squared. That's your 2x squared term. 2xy is simply 2 1 minus alpha times 2 alpha. But I'm going to have to remove this bracket and move it further on to make room for the whole function. In fact, can I erase it? Let's just erase it. There you go. Yeah, almost gone. And then 2y squared is simply 2 times 2 alpha squared. So I'm sort of laying it out to make it as clear as possible. Then minus 4x is minus 4 times 1 minus alpha, and minus 6. 6y is 6. 6. Okay, so all I've done is taken my expression for x3 in terms of alpha, substituted an f of x. So this is where keeping the function that you're minimizing near to hand with this calculation, otherwise you're trying to memorize. And so just a reminder, so the 2x squared gives this one, the 2xy term gives this one, the 2y squared gives this one, minus 4x gives this one, and minus 6y. So as I say, the basic machinery of these calculations is something you have done for ages. It's just a matter of getting it all in place, you know, all the little bits in place, and getting yourself organized. That's where the practice is with this sort of thing. So that equals 0 because we're minimizing the function along the trajectory. That's what we're doing. But of course the trajectory now is defined by this conjugate direction and not the other one. So that implies that d by d alpha, sorry, I'm using upright d by d alphas now. Okay, so this is written in partial terms because, you know, it's the most general way of doing it, but once we realize it's just a function of alpha, we can resort to upright d's. So there's a little bit of chasing of things here, but first of all, if we just figure out where all the alpha squared terms come in. So what have we got? We've got a 2 alpha squared coming from this term, this first term here. Yeah, and then we have a minus 4 alpha squared coming from here. Then we have 8 alpha squared. So is that for 8? We've got 8, 10 minus 4 alpha squared gives 6 alpha squared. And then we do the same with the alpha terms. So we get an 8 alpha now here from the second term. So this is from the alpha term from this quadratic, the alpha term from this quadratic, and the alpha term from this and it's alpha term from this. So there's a few more terms there, but once you put that all together, you will get minus 8 alpha, and then the final constant terms from this expansion is minus 2. So let's just get up to the next stage. So we've got d by d alpha of 6 alpha squared minus 8 alpha minus 2. Which implies that d by d alpha so this is just 12 alpha minus 8 equals 0. So it implies alpha equals 8 on 12, which is 2 on 3. Okay, so we've defined the trajectory in the S2 direction. We've now figured out what that is, and then and we write that in terms of alpha. So x3, remember, is 1 minus alpha 2 alpha. And now we've done the minimization of the function along that trajectory. I mean, it's no surprise because we're taking a 1D slice, 1D section through the function that we end up with a function in a single variable, and the single variable is alpha. We minimize with respect to alpha, and we find a value for alpha, which is 2/3. Now we just plug in the value. So we finish off this calculation, we plug in the value of alpha as 2/3, and we get 1/3, 4/3. Now, there's something magic here. Just as we finish up this section of the module, is 1/3 and 4/3 for x3 is exactly the minimum. Just keep an eye on the time. So what the conjugate method has done, by using the Hessian to find the two search directions, rather than endlessly going in orthogonal directions like gradient descent, it takes us exactly to the minimum. So it turns out the conjugate method takes just the dimension of the function. So in this case, it's a 2 in the number of steps. So and that's sort of a brilliant thing. And what I try and do in the last bit is of the lecture notes, it's a little bit more optional stuff. So in section 3.6, sorry, 5.6.1 of lecture notes provides a geometric interpretation of conjugate descent. But I'm not going to go into every step of it here, but if you're interested, you can read through it. Basically, what I take the interpretation from, so often this conjugate gradient descent is, in the literature, is just presented as a series of, of just, they present the method and then they say the conjugacy and they say, wow, it works. Well, actually, there was one author that I found who interpreted it in terms of the distortion of the function. So essentially, basically, your h transforms function. This is very much the very short-term thing, I guess, because it's not on the lecture videos this year. We it's not examinable, this bit, but it's just sort of to provide some sort of interpretation of understanding of why it works. So your understanding needs to be sort of at the level that h transforms a function to a space where it is more symmetric. So this process of inserting our Hessian function into the directions and making the directions less orthogonal has a correspondence geometrically, and I try and explain this just to round off for those who are curious. And this is going, as I say, this is going beyond the scope of this module, but it's what I always try and do is try and provide some sort of understanding aspects to things, and that's why I finish off with this section 5.6.1, and I'm sort of directing you as a reading exercise should you see more. It's what the Hessian is doing, because it has information in there about the shape of the function. It transforms you into a space where the function is symmetric again, and therefore you can converge very quickly. But I'll leave that more as a reading exercise. There's not many sections of this these lecture notes that I don't cover explicitly in the notes, but that's one of them. Okay, and I'll finish there with the amazing conjugate method. Let me, if I've got time, let me just show you again this picture to really summarize it. So the gradient descent is the black one, and it goes in successive steps. And it, of course, if I was to just carry this on, it would simply go in successive. It would carry on in perpendicular directions, and would take a relatively long time to converge. But the conjugate method, because we constructed it using Hessian, converges in two methods, so it adds extra information. And for that reason, more often in practical problems, you find the conjugate method being applied more than the gradient descent. But there are places where the gradient descent is sufficient for your purposes, and you'll see an example of that in your coursework in next term. So with that, I'm going to stop now.